Okay, so we started recording the session. Let's just wait for a few more people to join. Okay, Akshita is here. Morning, Akshita.
Good morning.
Yeah, morning. Okay, so while we wait for everybody to join, um, who is the class representative for the final years?
Right now,
Akshita,
Akshat, we haven't had the elections yet.
Oh, you haven't had the elections yet. Okay, so Akshat. Okay. Okay. So if the elections haven't happened, then that means even the MTechs also we won't know who the CR is. Okay. Because looking at the attendance, I'm not sure exactly how many people have enrolled and how many are continuing with the with the classes. So anyway, let's just wait for a few more to join. Okay, good morning, Shantanu. I have a question for you, Shantanu. Please, left the call. Only girls. Shantanu, can you hear me?
Yes, sir. Yes, sir.
I have a question for you.
Yes, sir.
So, is there, have you guys elected the class representative for the MTechs?
Yes, our class representative is ये sir बुला रहे हैं. Yes, sir. He's here.
No, no, what is this person's name?
Shekhar, sir.
Shekhar. Okay, I'll send an email to you, Shekhar. I just want to uh, confirm
Yes.
who
Yes.
or not.
Yes.
How many people
Yes, sir.
are still in the course? Has anybody left the uh, program? Any idea?
Uh, sir, can you repeat just?
How many MTech students are continuing in the program? Has anybody left the program? Usually, sometimes after the
Yes, sir.
first.
One have left the program. 11 are
Okay,
continuing.
11 are continuing. Okay, very good. Thank you. Okay, let us get started. We've got quite a few people here. So today we are going to start talking about Darcy's law. You can please go back to mute. Mute. Before I forget. So in case you have a question while I'm presenting, if you raise your hand, I'm not able to see it when I'm in presentation mode. Okay. So the ideal way, if you want to stop me and if you have a question, is to unmute yourself and just say, just stop me. Okay. Because raising your hand somehow, I'm not able to see it on the screen when I'm in the full screen mode. So that makes it a little bit difficult. So I think last time somebody raised their hand, I didn't see it. And then by the time I came out of the presentation mode, it was the end of the class. So then the question couldn't be addressed. Okay. So if you have a question, please unmute yourself. All right. So that's going to be the kind of standing instructions for the rest of the time that we are doing this online. Okay. All right. So we are going to be talking about Darcy's law. All of you are familiar with it already, but just to give you some brief historical background. Now, this Darcy, this person, Henri, Henry Darcy, was a French scientist who was in charge of the water supply in a French city called Dijon, Dijon. Okay, so and then in the process of trying to understand the water supply in the city, which came from some springs, from underground springs in the city of Dijon, he did some experiments, and then that's when he observed this. So the year that this was observed is 1856, close to 175 odd years since this has been observed and well known in practice. It continues to be the fundamental law that applies to groundwater flow. Okay, so what Darcy did was take a, let's say we'll take a cylindrical sample, fill it up with some sand, let's say, okay, and flow some water through this cylindrical sample. Now remember, this cylindrical sample is cylindrical soil sample. Okay, it's got soil filled inside it. I'm just going to draw some soil particles inside. Just imagine this whole thing is filled with soil. I'm not going to be able to draw so many soil particles. Okay, and then what Darcy did was to install a couple of piezometers in this sample. Okay, let us say these piezometers are a distance of L, capital L apart. Okay, and he observed the total head in these. So let's say this is my datum. Okay, so this point, let's say the head at this point is H1, and the head at this point is H2. Okay, so what Darcy found was that this Q, the flow rate Q that was going through this soil sample, of course it was coming out the other side. Okay, I have not drawn the arrow coming out here. Okay, the flow is going in on one side and coming out of the other side. And so if I maintain a certain value of Q and I maintain this H1 and H2, right, what he found was that Q was proportional to let's say was proportional to H1 minus H2, or you can say H2 minus H1, either way is fine. Okay, H1 minus H2 and inversely proportional to L, this length L between the two piezometers. Okay, so if you keep L constant, then Q was proportional to H1 minus H2, and if you kept H1 minus H2 constant, this Q was inversely proportional to L. So if I, for the same H1 minus H2, if I increase the L, Q would decrease, and if I decrease the L, Q would increase. Right. So basically, in other words, Q, what this H1 minus H2 by L is giving us is the head gradient in the direction of flow. Right. Q is basically giving us the head gradient in the direction of flow. Okay. Now, I can also write this in a slightly different form as dH by dx. Okay, instead of writing it as H1 minus H2 divided by L, in general, I can write it as dH by dx. Okay, which means the hydraulic gradient in the direction of flow. Now, based on our conventional way of defining dH by dx, right? How do we define dH by dx? We define it as H2 minus H1 divided by X2 minus X1. So in order to account for that, you'll just have to put one negative sign here. Okay, that's just because of our mathematical convention of how we describe the term dH by dx. I hope that's clear, right? dH by dx is classically defined as H2 minus H1 divided by X2 minus X1. So the numerator will be negative because H2, as you can see, is less than H1. So H2 minus H1 will be negative. X2 minus X1 will be positive because X is increasing in the direction of flow. So X2 will be larger and X1 will be smaller. So X2 minus X1 will be positive. So the numerator will be negative and the denominator will be positive. Now, so you'll get a negative number. To correct for that, you just put a negative sign. So you get a positive number on the right hand side, because flow rate cannot be, physically it's not possible to have negative flow rate. Of course, you can mathematically understand it, but anyway, so Q is proportional to minus dH by dx, right? The way to think about it physically, is that the flow is happening in the direction of decreasing energy. That can be one way of physically interpreting the negative sign, right? What is H? H is basically the total head at point 1 and at point 2, right? So the total energy at point 1 is greater than the total energy at point 2, right? And the flow is taking place in a direction where the total energy is actually decreasing. And since that dH by dx is basically giving me the gradient of that energy, so you can think of that negative sign as indicating the fact that flow is happening in the direction of decreasing energy. That could be a physical interpretation for that negative sign. Okay, all right. Now, one more term that I can add to this is that Q is also proportional to A, the cross-sectional area of the sample, right? So if I maintain the same dH by dx, and if I take a sample with the larger cross-sectional area, I'll get more flow for the same gradient. Or if I take a smaller cross-sectional area, I'll get lesser flow for the same gradient. Now that also seems fairly obvious, right? If I increase the cross-sectional area, so this is my cross-sectional area. If I increase the cross-sectional area and keep everything else constant, Q will be higher. And if I decrease the cross-sectional area and keep everything else constant, Q will be lower. So that's nobody can disagree with that. That seems fairly intuitive, right? So that's what Darcy observed. This is based on experimental evidence, right? And then to get rid of this constant of proportionality, get rid of this proportionality, you introduce this constant of proportionality. You get Q equal to minus K times dH by dx. What happened? Minus K dH, oops, times K. Okay, and so this K, which is the constant of proportionality, is basically some property of the type of soil that I have filled in there. And this K is called the hydraulic conductivity. Now, I'm sure everybody here has heard of this, either in a geotechnical engineering class or in a water resources engineering class that you did in your BTech. You must have heard all of this. You're pretty familiar with this, right? So Q equal to minus K, where K is the hydraulic conductivity, times dH by dx, which is the hydraulic gradient in the direction of flow, times A, which is the cross-section area through which the flow takes place. All right. Any questions? Don't simply raise your hand. I can't see it. Please unmute yourself.
Sir,
Yes.
we can say that velocity is directly proportional to velocity gradient I. B is directly proportional to I. Then B is equal to Ki after omitting the proportionality concern. And then B equal to Ki, we know that from the continuity equation, Q equal to a V. Q
Okay.
equal to a V, and V we put Ki.
Sure.
Then Q equal to Kia.
Absolutely. So yeah, so you're familiar with this. Everybody has learned Darcy's law probably in geotechnical engineering in your BTech, right? So
Yes,
this is not something that is brand new information for most of you, I guess. Anyway, that's good. Yeah, correct. The only difference is you have to be a little bit careful with the way you describe that velocity. You use the letter V. By convention, we don't use V in groundwater hydrology. I don't know what the convention is with respect to geotechnical engineering, but when it comes to groundwater hydrology, we don't refer to V. V means something slightly different. Okay, so let's just pay attention to this. Okay, so I don't disagree with what you've said. More or less, you and I are in agreement. So let's keep going. Any other questions?
So I have one more.
Go ahead.
What are the factors on which the hydraulic conductivity depends for
What are the
different
factors on which K
surfaces?
depends? What are the factors on which K depends, right?
Yes.
Okay, we will come to that. Just wait for 5 more minutes. We'll be talking about the factors on which K depends. Okay, we'll come to that. It's of course a property of the type of soil that you have and so on, but we'll get into a little bit more detail. Don't worry. Yeah, any other questions before we move on? Okay, no other questions. Let's keep going. So what we have written as Darcy's law is Q equal to minus K, and you used I times A. Now where I is nothing but dH by dx. This is another short form for writing the same equation. What I'm going to do next is to divide both sides by the cross sectional area. Then I'll get Q divided by A equal to minus Ki. Okay. Now this capital Q divided by capital A, sometimes we denote it, not sometimes, we denote it by the letter small q equal to minus Ki. Okay, K times I. K being the hydraulic conductivity of the soil and I being the hydraulic gradient through which the flow is taking place. Now, what are the dimensions of Q? It will have dimensions of L cubed T minus 1, right? Volumetric flow per unit area per unit time, right? This area of cross section is L square. Gradient does not have any dimensions because it is dH, which is L divided by dx, which is also L. So I has got no dimensions. So K must have dimensions of Lt minus 1 in order to make this equation dimensionally homogeneous, right? I have L cube T minus 1 on the left hand side. I must have L cube T minus 1 on the right hand side as well. So therefore, K, the hydraulic conductivity, is going to have units of L T minus 1. Okay. Now, in the second equation that I wrote, where I replaced this capital Q by A with small letter q, now I have equal to minus Ki, and therefore this small letter q must have dimensions of Lt minus 1 because K has Lt minus 1 on the right hand side and I does not have any dimensions. So this q has dimensions of Lt minus 1. In honor of Darcy, this q is referred to as Darcy velocity. Oops, sorry. It's denoted by. Now you might wonder, why is it called velocity? It is called velocity simply because it has the dimensions of velocity, and the word Darcy is there because we are honoring the scientist who discovered this phenomenon or who observed this phenomenon for the first time, right? So q, small q, has the dimensions of velocity and therefore it is referred to as Darcy velocity. Now it is important to keep in mind that this term that we refer to as Darcy velocity does not represent the velocity of the water flowing through the soil sample. Right? Now it might seem counterintuitive. If it's not representing the velocity, then why would you call it velocity? Just because it has units of velocity? And then the second question is, why doesn't it represent the velocity of the water particles? I'm taking the flow rate Q, dividing it by the cross-sectional area through which the flow is going, and then I'm getting the Darcy velocity. It has dimensions of velocity. Seems fairly reasonable to call it Darcy velocity, no problem. But I am going one step further and saying, although it has the name Darcy velocity in it, it does not represent the actual velocity of the water that's flowing through the sample. Why not?
Because the pressure head is very low in the soil. So only we consider the velocity.
No, actually, the velocity head is very low, right? We cannot comment beforehand on what the nature of the pressure head will be, but we do know that the velocities are very low. Okay, but the question is, let us say this number Darcy velocity, you get it in some you get, let's say, 1 meter per day or 3 meters per day or 0.1 meters per day, whatever that number turns out to be. I'm saying that number is not the actual velocity with which the water is passing through this sample. So now I've just done a cross section of this cylindrical sample, let's say. What you have to keep in mind is that the water is not flowing through this entire area. This water is actually flowing, let's say there are so many different soil particles. I'm just exaggerating the soil grains, right? So there are so many soil particles here. The water flow that's taking place is not going through this entire area. It is only going in the gaps in between the soil. So when I say A, it is the total area of this. So if the diameter is D, area will be pi by 4 d square. But is the water flowing through this entire area A? No, it's not. It is only flowing through that area that is present in between the soil particles through the pores, right? Now, if it was a pipe, the water would be flowing through the entire area, and therefore, when I divide the discharge Q by the area of cross section, I get the average velocity of that cross section, right? But in the case of a soil sample, that area is not actually the entire area through which the water is flowing. The water is flowing through a fraction of the area. Does that make sense?
Yes, sir. Yes, sir.
Okay. So the Darcy velocity does not represent the actual velocity with which the water is flowing in the pores. Okay. So if I want to find out the actual velocity, that velocity is referred to as the pore water velocity. Pore water velocity. This one I refer to it with the letter small b. Okay, how do I get this? It is some function of q, this Darcy velocity. What should I do to get this? First of all, now my question will be, will this pore water velocity be less than Darcy velocity or more than Darcy velocity?
Sir, it is same because whatever the water flow through this area, this only flow through this pores. In my point of view, it may be same.
Okay, so in that case, then we don't need another term called pore water velocity. We can I've just written v equal to q. I've not completed the equation. The equation is not complete. Okay, I need something else to modify this equation. Okay, so if that was the case, then I don't need another term, v, pore water velocity. I can simply call it Darcy velocity and then I'm done, right? So there is something a little bit more to the story. Now just imagine a pipe which does not have any soil filled inside it and the water is flowing through it. I know the flow rate of the water. I divide it by the cross-section area of the pipe. I will get the average velocity through that cross-section. Now, instead of having a hollow pipe, I have filled that entire pipe with soil. And now some water is flowing through it. Okay. And I have some flow rate. And I know the cross-section area of the pipe. But there's no use of knowing the cross-section area of the pipe because, well, okay, I won't say no use. It's only limited in its use. I also need to know something else about this cross-section area. What proportion of this area is filled with soil and what proportion is filled with pores? Thank you. Yeah, this is the problem when we have multiple people sitting in the same classroom with all of you listening to the same thing. So this echo thing happens. Sorry about that. There's not much I can do. Well, anyway, so the way to correct it would be to divide this Darcy velocity by the porosity. What is porosity? Porosity is volume of voids divided by volume of the sample. Now,
Total volume.
yeah. So you can make a reasonable assumption that at any given cross section, the area of voids as a ratio of the area of this total cross section is approximately the same as the porosity which is a volume phenomenon, and now we are talking about an area phenomenon, a surface phenomenon, right? We can make a reasonable assumption that the fraction of the pore area in this cross section is about the same uh, as the porosity of the sample, right? Of course, it's a matter of relating areas to volumes, and we can make a reasonable assumption that these two can be related more or less, assuming the soil is more or less homogeneous. I don't have drastically different soil within the same soil sample, right? Assuming the soil is more or less the same and more or less homogeneous, we can make this assumption fairly reasonably well. Okay, so the pore water velocity will always be greater than the Darcy velocity, because porosity is always going to be less than 0.5 or it will be around 0.2 to 0.4. That's the general range of values. So V, the pore water velocity, will always be greater than Q. It will not even be equal to Q, not possible, right? It will always be greater than, at least 2 times, 3 times, and so on, right? If it's N is 0.5, then it will be 2 times. If it's 0.33, it will be 3 times, and so on. Okay, so this pore water velocity actually tells us how fast the water is moving. Okay, did somebody raise their hand? I heard one. Yeah, Shantanu,
Yes,
you'll
sir.
have to unmute yourself. Go ahead.
Sir, we study in BTech in geotechnical engineering. Maybe seepage velocity is the pore water velocity here.
Okay, yeah, same terminology. Okay, so you called it seepage velocity. Okay, no problem.
Yeah, that's why we know seepage velocity is equal to Vs equal to V by N.
Okay. Oh, so you called it V equal to V by N.
Yes, then it
Okay.
will be okay. Vs is greater than V, and here
Okay.
Vs is pore water velocity.
Yeah, no problem. This is just a usual thing, right? Different people follow
Yes.
different books, different symbols, and so on. I prefer to use this, so it doesn't matter. Okay, as long as we understand the concept, it doesn't matter. Seepage velocity is probably another name for the same thing, pore water velocity. No issues. Okay. Okay. Any other questions? Okay, great. So now let's now. So there was a question about what is the what are the factors on which this hydraulic conductivity K depends. Okay, so we are going to do a thought experiment. Okay, now I'm going to say that, let us say we go to the lab and say, I want to recreate this Darcy's law in the laboratory and try to find out what are the factors on which this hydraulic conductivity depends. So what I'm going to do is take some perfect uh, soil samples. Okay, now when I say a perfect soil sample, what I mean is I'm going to take uh, glass beads, BEADS, of same diameter. Okay, so if you go to the market, you can buy these small glass beads, all of them of the same diameter, let's say 2 mm or 3 mm, 4 mm, whatever it is. I go to the market and purchase glass beads of the same diameter. I take them and dump them into the into that cylindrical specimen, and I repeat the same test again in the laboratory. Okay, then what I notice is that this, like we wrote this, right? What is that? Minus dH by dx times A. Now, this dH by dx and A, there's nothing much you can do. And if I increase the cross-section area, there'll be more flow. If I increase the gradient, there'll be more flow. If I decrease the gradient, there'll be less flow. If I decrease the cross-section area, there'll be less flow. That's fairly obvious, and nobody can disagree with that. Now, what I do is I try filling glass beads of different diameters each time I run the experiment. Okay, I try once with large beads, I try once with smaller beads, keeping everything else constant, and then I want to find out what happens, right? So we already know this expression, minus K dH by dx times A. But when I repeat this experiment in the lab, okay, I find that this Q is proportional to d square, the diameter of the bead. right? So if I increase the diameter of the bead, then my Q scales as d square. Okay. Everything else remaining constant, dh by dx remaining constant, a remaining constant, and so on. Okay. Then now we will talk a little bit about something that is not very uh, very convenient to think about. Let's imagine that I take a certain glass bead of a certain diameter, okay, and then I change the fluid that I'm passing through this uh, through this setup, right? Once I try with water, once I try it with milk, then the next time I try it with honey, next time I try it with I don't know, ethanol, next time I try it with glycerin. I try different fluids, okay, with basically, which means fluids have their own properties, right? So I have what are the two basic properties that you can think of for a fluid? When I describe fluids, milk, water, honey, uh, alcohol, petrol, diesel, all of these different fluids. Go ahead.
Permeability decreases. Oh, permeability, that means hydraulic conductivity.
Okay, decreases with what?
That means we found from the uh, Kozinski-Curwen's equation 1 k equal to 1 by kk gamma by mu eq by 1 plus e d square. Here we can get q is directly proportional to d square. And k depend upon several factors like Terzic equation k equal to 200 e square d square, consolidation equation k equal to cbmb gamma w.
Yeah. Shantanu, no, I'm forget about the equations for a minute. Okay, let's try to understand it physically, right? Uh, as soon as you start giving me an equation with more than two terms, I I'm already lost because it's hard to memorize all these things. I'm trying to understand it physically. Okay, so let us imagine this. Let us do this thought experiment. Okay, so let us say I have water and I have honey, two kind of extremes. Okay, and let us say that I'm getting the same discharge with the same, and I'm keeping the diameter of the bead the same. Okay, I have the same head gradient, same cross sectional area, same same diameter glass bead. Okay, in one case I have water, in another case I have honey, let's say. Okay, everything else remains the same. The diameter of the glass bead is the same. The gradient is the same in both cases, which means dh by dx is the same. The cross sectional area is the same. In which case do you think there will be more fluid going through?
In water, sir, because viscosity of water is less, but viscosity of honey is more.
Exactly, right? So, which means this Q must be inversely proportional to mu. That's what you're saying,
Yes, sir.
right? So Q is inversely proportional to mu. I'll use dynamic viscosity, which is the one of the fundamental properties of a fluid, right? So I have Q being inversely proportional to the dynamic viscosity. Now, imagine I have a. It's very difficult to imagine, but let us say I have a fluid, two fluids. Actually, I mean, I really cannot imagine this, but another property that is kind of fluid property that's important is the density. Okay, so what people have observed is that this Q is proportional to the density of the fluid. So the greater the density, the greater the flow. The lower the density, lower the flow. Everything else remaining constant. It's hard to imagine rho and mu are kind of interrelated properties, right? So what we will do is, we will, instead of writing these as uh, separate parameters, what I'll do is I will write it in this format. I'll write it rho g by mu. Now this has sound backing from what you can say as what is that from fluid mechanics, where this rho and mu being rho because it carries the impact of let's say velocity, because it's carrying mass with it, because rho times volume will give you mass, so it has inertia on the top, and mu being the viscous forces, so you have inertial forces on the top and the viscous forces in the denominator. So that is the kind of uh, theoretical backing which we have from the point of view of fluid mechanics. We'll not get into a whole lot of detail on this, right? So we can say, broadly speaking, that this Q is proportional to the unit weight. Rho g is unit weight, and it's inversely proportional to the viscosity of the fluid, right? So this being the case, and then all other things are still the same. Q is still proportional to dH by dx. It is still proportional to A, right? So now I can write a modified form of this equation, Q proportional to d square rho g by mu times dH by dx times A, right? So this is, now this experiment can never really be done with different fluids, right? I mean, I won't say never. It's difficult for us to imagine doing this because the amount of different fluids you would need is so huge that it becomes difficult for us to imagine. Maybe you could try with water and salt water. That's about the most you can try. Nobody's going to get liters and liters of honey and run this experiment, or liters and liters of milk and run this experiment, right? So it's a thought experiment, more or less. Okay, but then I want to be able to correlate this with whatever we already know about Darcy's law, which is this Q equal to minus K dH by dx into A, which means this term that we have here must in some way be connected to my hydraulic conductivity, right? So therefore, to introduce the constant of proportionality, we'll call this K equal to C d square rho g by mu, and this C d square, I'm going to call it a new term. I'll call it small k, k rho g by mu. So this is a fundamental expression telling us what the factors are that determine the hydraulic conductivity of a soil sample. Now, the hydraulic conductivity of a soil sample is both a property of the soil, which is denoted by this C d square, and a property of the fluid which is flowing through that particular soil, right? So hydraulic conductivity depends not only on the soil, but it also depends on the type of fluid that's flowing. Now, this might not be very relevant in cases where I just have groundwater flowing, but suppose I have a region where there is salt water that comes in contact with fresh water underground, right? And this happens along the coastline. India has a very long coastline, right? So wherever there is this interface between fresh water and salt water, then this hydraulic conductivity, depending on the nature of the fluid that is flowing, also starts to play a role. Most of the time, right? Most of the time, we don't deal with problems which involve fluids of different densities, right? So it's only limited to regions where there is salt water coming in contact with fresh water. There are other possibilities also. Suppose there is some contaminant that has entered into the ground. So, for example, if there is contamination due to leakage of some petroleum products, right, which may have different density, which may have different viscosity, so they will flow with a different compared to water flowing. Petrol or diesel or any other material which has a different viscosity and a different density will not flow in a manner that is similar to how water would behave, right? So therefore, this hydraulic conductivity is a property that depends both on the nature of the soil through which the flow is taking place and the nature of the fluid that is flowing through that soil. Okay, so now when I say the nature of the soil, right, the only parameter that determines the hydraulic conductivity when it comes to the soil is basically the diameter of that soil, the diameter of the particles of that soil, right? So the larger the diameter, the larger the hydraulic conductivity of that soil. The smaller the diameter, the smaller the hydraulic conductivity. Okay, so now I introduced this new parameter small k. Now there is a lot of confusion in between geotechnical engineers and groundwater hydrologists, right? They like to call capital K as permeability, coefficient of permeability, and they'll call the small k intrinsic permeability. Okay, so the small k, it's called the intrinsic permeability. Okay, because it is the diameter of a soil is an intrinsic property of that soil, right? So it is intrinsic to that soil, and therefore it is referred to as intrinsic permeability, and it has units of L square. C is some kind of shape factor that depends on the nature of the shape of the particles of that particular soil. If the particles are rounded, then you will have a certain value of C, and if the particles are not so well rounded, then you might have a different value of C. But generally speaking, this K is strongly dependent on the particle size, and what particle size to use is also something that there's different kinds of formulas available. Sometimes people use D10, sometimes people use D30. Okay, for those of you who are not familiar with D10, D30, D10 is the diameter of 10%, diameter at which 10% of the soil particles are retained on a certain sieve, right? Is that correct? 10% retained or 10% passing?
Retain.
10% retained. So you have different sizes of sieves through which the soil passes, and then the sieve on which 10% of the soil by weight is retained is called the D10 of that particular soil, or D30 would be 30% that is retained on a particular sieve, right? So that is how we define the intrinsic permeability of the soil, which has dimensions of L square, right? So small k has dimensions of L square. Rho is L cube T minus 1. G is LT minus 2 meter per second square. And then mu is ML minus 1 T minus 1 if I... Oh, wait a second. What happened to... Oh, K rho G by mu. Did I miss something? L cube T minus 1. How stupid. It's ML minus 3. Nobody corrected me. That was a test for you guys. Yeah, rho, the density is ML minus 3. I was wondering how come there's an extra M. Okay, so mu has dimensions of ML minus 1, T minus 1. That's kg per meter per second, if I remember correctly. So the M cancels out between the numerator and denominator, and then you rearrange the terms, you will get capital K with LT minus 1. Okay, so that should be fairly straightforward. Okay, so capital K, we are going to call it hydraulic conductivity. Geotechnical engineers will continue calling it permeability or permeability coefficient or coefficient of permeability. I don't care. In the groundwater hydrology course, we will call capital K as hydraulic conductivity and small k as intrinsic permeability. This problem is never going to be resolved. I have discussed this with so many people, and textbooks there's confusion. Different practitioners have different opinions on this. Doesn't really matter. Now the groundwater hydrology textbooks pretty much agree that capital K should be hydraulic conductivity and small k should be intrinsic permeability. It's just a naming convention. Doesn't matter what you call it as long as you understand what it is. Okay. All right. So any questions on this? So what I've done is basically I've just described to you that hydraulic conductivity does not depend only on the soil. It also depends on the fluid that is flowing through it. Okay. So when I say fluid properties, I mean the density and the viscosity. And when it comes to the soil properties, we have found a convenient proxy for it by saying only the diameter of the soil matters. And that helps me figure out what the intrinsic permeability of the soil is, which becomes a parameter in this equation K rho G by mu. I put in that value of K, I will get the capital K, which is the hydraulic conductivity of the particular soil sample. Okay. All right. So now let's move on. Let's just quickly probably solve this problem, and then we'll see how much time we have to go on. Okay, a field soil sample is packed in a test cylinder of length 50 centimeter and diameter 6 centimeter. The sample is tested for a period of 3 minutes under a constant head difference of 16.3 centimeters. As a result, 45.2 centimeter cube of water is collected at the outlet. Determine the hydraulic conductivity of the sample. So it's fairly straightforward, right? So now for the purposes of this problem, I am going to get rid of this negative sign, simply because the negative sign, you know that it's only a mathematical, uh, uh, you know, it's just a mathematical negative sign there. It doesn't necessarily carry any physical meaning as long as you use it correctly, right? Because it directly gives you head difference. Instead of writing H2 minus H1 as minus 16.3 and then you multiply it by a minus 1, doesn't really matter. So you can just directly go ahead and figure it out. So the question is, what is the hydraulic conductivity? So K is unknown. So I'll keep K over here. The head difference is 16.3. And the distance over which this head difference is taking place, although it's not mentioned very clearly in the problem, the only length that I have is the length of the soil sample, which is 50 centimeters. So I'm going to put 50 in the denominator here. And then I multiply that by the area of cross section of the test cylinder. So it's pi by 4 d square, pi by 4 into 36, that's 6 square, 36. And then I have the Q on the other side, which must be, so the sample is tested for a period of 3 minutes. So in 3 minutes, I'm collecting 45.2 centimeter cube of water. So here I have, this is centimeter square. This one has no units. 16.3 is centimeter, 50 is also centimeter. So it cancels out. So I will write this as 45.2 centimeter cube divided by 3 minutes. I'll write that as seconds, 180 seconds. Okay, so I'll get the answer in centimeters per second, which is a very clean unit, very neat way of writing the hydraulic conductivity. After this, you just solve it, rearrange the whole thing, you will get the value of K. Okay, I'll leave that as an exercise for you to do. Okay, any questions before we move on? Okay, let's go on. So now there are, I'm not going to describe these two methods. These are something that you can find in any textbook if you have gone through this. There are these laboratory methods for estimating the hydraulic conductivity. Now again, the problem comes, right? The tests are called the constant head permeability test and the falling head permeability test. Now again, the problem is that these tests are typically done in a geotechnical engineering course where the word permeability is used. But for the sake of this, we will only in this context, we are going to use the word permeability to mean capital K. Okay, please don't worry about it. So you've all done this earlier, or you can easily look this up in any textbook. It will give you some equations for estimating the K for a constant head permeability test and a falling head permeability test. Now, I will ask one question, which we can, those of you who remember the procedure for this, can you tell me in which case would it be better to perform a constant head permeability test? For a soil sample which has got a high hydraulic conductivity, or a sample which has got a low hydraulic conductivity? In which case would it be better to do a constant head permeability test compared to a
For constant head permeability test, we prefer coarse grain soil, and for falling head permeability test, we prefer fine grain soil.
Why is that?
Sorry,
Why?
because for falling head permeability test, the test is conducted in a soil sample from given time T1 to T2 or T2 to T3. So time foundation is there. And for yes, sir.
Okay, so you're saying for a constant head permeability test, it's better to do it, or it's better suited for coarse grain soil, which will have higher value of K, versus a falling head permeability test, which would be done for a fine grained soil, which would have a lower value of K. Correct? I think it's the other way around. So just go back and look this up, right? This information is like freely available. Look it up and let's discuss this in the next class before we move on. Okay, I think we are just running short of time. Yeah, we ticked over. All right. So see you all in the next class tomorrow. Who was the class representative again? Did you say Shankar or name starting with S?
Shekhar, sir.
Shekhar.
Gautam Shekhar.
Gautam
Yes.
Shekhar. Okay. Thank you. I'll send you an email, Shekhar. Thank you very much.
Yes.
Thank you, sir.
Yeah. Take care, everybody.